Hello everyone. Am I audible? Hello.
Yes, sir.
And the slides are also visible?
Yes, sir.
Okay. So let us, try to catch up with what we have done in the last class. So we started with the forced convection, and what we said in the last class is, in case of forced convection, there is a flow of the fluid is also taking place. And in such cases, one has to solve the velocity problem first and then the heat transfer problem. So, when it comes to formulating the problem is easy because you can, do the shell balance and obtain the required, partial differential equations or algebraic equations, whatever is needed there. But the challenging part is to solve these equations. It's not about the formulating. You can formulate it easily, but it is really difficult to solve these formulated, partial differential equations. So that you probably have, understood in your transport phenomena also, isn't it? So one of the way people use to circumvent this problem is to use the heat transfer correlations. So heat transfer correlations are the correlations based on the experimental data. Again, you can directly calculate the value of heat transfer coefficient without solving the velocity problem. So that ease out your heat transfer problem significantly. But the disadvantage in this case is your error will be in the order of 25 to 30%. Okay, but you can solve the problem easily because you don't have to look at the momentum transfer at all. You can directly obtain the transfer coefficient in which the effect of velocity, effect of the change in the properties, everything is built in. Okay. One of the easiest way to look at these problems is to look at the boundary layer. So that is what we have seen in the last class. This is the typical boundary layer flow shown here. Here you can see uh, uh, there is a flat plate, and around this flat plate the fluid is flowing with a free stream velocity of v. And again, the fluid element which are exactly in the contact of this particular plate, the velocity becomes zero. And as we move along the x direction from this leading edge, the thickness of this boundary layer increases where there is a velocity distribution present. So at the bottom here at the plate, the velocity is zero, and as we move in the upward direction, the velocity approaches to the free stream velocity. Okay, so there are three layers in the boundary layer: a laminar boundary layer, transition zone, and the turbulent boundary layer. So as we were arguing that most of the resistance present for the heat transfer is always because of the thin layer of fluid which remains stagnant near the wall. Okay, so clearly the laminar boundary layer which corresponds to the heat transfer resistance. And also as we move beyond the laminar boundary layer, you can clearly see that in the transition zone and the turbulent zone there is the eddies, and the wake formations are taking place, and because of this turbulence, the heat transfer in this particular region you are going to see a higher heat transfer rate compared to what we see in the laminar boundary layer. So as the thickness of the laminar boundary layer increases, my heat transfer coefficient first decreases, and then as we move in the transition zone or in a turbulent zone, my heat transfer coefficient starts increasing. So there is a critical Reynolds number when we are looking at the flow across the flat plate. Flow across the flat plate, the critical Reynolds number is 5 into 10 raised to the power 5. If my Reynolds number is less than this particular limit, then I am going to have a laminar boundary layer. Beyond it, I will have between 5 into 10 raised to the power 5 to 10 raised to the power 6. In this region, I am going to have a transition zone, and beyond this, we will have a turbulent zone. Okay. So in order to extend this concept of boundary layer to the heat transfer, in case of heat transfer, we also have a thermal boundary layer. So if suppose the temperature of this plate is Ts and the temperature of the free stream is T naught, there is a distribution of the temperature taking place between this boundary layer. Again, one more point to note down here is this laminar, this thermal boundary layer and this momentum boundary layer are two different boundary layers. These are not same. Okay, so thermal boundary layer uh, is within the momentum boundary layer when the Prandtl number is greater than 1. If the Prandtl number is less than 1, the momentum boundary layer is within the thermal boundary layer. Okay, and when Prandtl number equals to 1, momentum boundary layer and the thermal boundary layer both coincides with each other. So a typical example is a air. So air has a Prandtl number around 0.69. So in this case, you can see the momentum boundary layer is within the thermal boundary layer, the way it is shown in the figure. But that is very close to the thermal boundary layer. So in most of the cases, people generally assume that thermal boundary layer and the momentum boundary layer are coinciding with each other in case of air. Okay, so here one more important number we have started looking at, that is the Prandtl number, which is nothing but kinematic viscosity divided by the thermal diffusivity. So this particular number is important. So we will see details of this later today. Okay. So this is the same concept as I said, that the heat transfer coefficient is not constant when we are looking at. So here you can see along the theta direction heat transfer coefficient or a Nusselt number. Nusselt number in this case is hd by k. So clearly d is constant, k is constant. So this also gives me a same picture corresponding to the heat transfer coefficient. So I can clearly say here that the heat transfer coefficient decreases first as the thickness of the laminar boundary layer increases till the separation point here. Once the separation point, beyond the separation point, there is a eddies and wake formations are taking place. So because of turbulence, the heat transfer coefficient further starts increasing. So in general, whatever the correlations people write, these correlations in general account the average value of heat transfer coefficient. So we don't have to look at this local effect. We can directly use the average value of heat transfer coefficient multiplied by area into temperature difference. That is going to give me the rate of heat transfer by Newton's law of cooling. Okay. And if other resistances are there, this average heat transfer coefficient will be used to calculate the overall heat transfer coefficient. That's it. So average value of heat transfer coefficient is used, which further simplifies analysis of the heat transfer problem. Okay.
Hello, sir.
Yes, please go ahead.
Sir, can you please explain what it means when it says the thickness of boundary layer increases? So
Can you
there
see here?
only. Yes, sir.
As we move along the x direction, you can see the thickness in the upward direction is increasing, isn't it? Up to this, there is a laminar region itself, isn't it? Up to this, there is a laminar region itself, isn't it? So as the thickness of this boundary layer is increasing, more resistance is going to increase, isn't it? Because this particular layer, the laminar layer, most of the resistance to heat transfer is offered by this particular layer, isn't it?
Yes, sir. Yes, sir.
Is it all
So,
right?
are we saying that as the we
As the
know that the
distance from the
input,
leading edge is increasing, as the distance x from the leading edge is increasing, which is clear here, as this distance x from this leading edge is increasing, initially in the laminar zone, my boundary layer thickness is increasing up to this. Beyond this also it is increasing, but the problem is beyond this there is a turbulence formation. Isn't it? Beyond this, there is a turbulence formation is taking place in a boundary layer, and therefore instead of decreasing the rate of heat transfer, it rather increases. Is it clear?
yes, sir. Somewhat.
Still not clear?
So, what's the physical meaning of this boundary layer? What is this boundary layer we are talking about?
So see, this boundary layer is in a way here it is. You can see more details you will cover in the fluid mechanics, but I am still giving you some picture here. Okay, so there is a free stream velocity here. So near this wall surface here, because of no slip condition, the velocity is going to be 0. Is it all right?
Yes, sir.
And the velocity here
Sir, is a pointer moving?
Yes, I am moving.
Yes,
It's
sir, your
not moving.
pointer is visible.
I'm not able to. At
I
least
think
maybe it's some problem at my end in that case.
yes, probably internet connection at your end might not be well. Okay. Anyway, okay. So as we move along the upward direction here in a y direction, here you can see here at the bottom it is velocity equals to 0. But as we reach to the this particular boundary layer here, the velocity basically is equals to the free stream velocity. So what is boundary layer? Boundary layer is basically gives me a region in which there is a velocity distribution is present. Okay,
Yes, sir. It's the viscid region beyond which there is the inviscid region.
correct.
All
Yes,
right.
yes.
Sir, you are talking about the developing fluid, na? Or is it fully developed fluid?
This beyond this there is a fully developed flow. Beyond this plate there is a fully developed flow. There is no wall effects are there. Is that what you wanted to say? Before this plate.
Sir, this separation, that is boundary layer, you
Uh,
are talking about the fully developed flow or developing flow? I am asking that.
See, when you say a fully developed flow, basically what you wanted to say is, see, this concept of fully developed flow comes basically is what? How far are you from the, starting of the pipe, isn't it? That is what it is, isn't it? So can you neglect the wall effect or something? That is what you consider in a fully developed flow, correct?
Yes,
So
sir.
what I wanted to say here is on the left hand side here, this there is no velocity profile is not there, isn't it? There is constant velocity is there throughout, isn't it? As I have shown by arrow, isn't it? So
Yes,
it's a
sir.
fully developed flow here on the left hand side. But if you look at this boundary layer here, there is a disturbance of the flow is definitely there. Okay. So
Yes.
I can say that on the left hand side of this plate, there is a fully developed flow, definitely.
Okay, sir.
Okay. Okay. So now as we were discussing that, uh, our analysis is going to get simplified immensely if we use the correlations for the heat transfer coefficient, because that is going to account the velocity distribution. It is going to account the effect on the change in the properties, everything, correct? And because of that, I just have to write a Newton's law of cooling and find out the rate of heat transfer. I don't have to do anything more than that, isn't it? That is what it is. Uh, but then the another question comes in our mind is when we are saying the correlations, what type of correlations are we talking about? Are these perfectly black box type of correlations, that means purely a data based, or these are having some physical significance behind it? Okay, so these are the questions which we are trying to answer in the dimensional analysis. So what I'm trying to emphasize here is the dimensional analysis gives me pinpointedly for a given system, if we know or if we have identified that the relevant variables and parameters and properties correctly, in that case it is possible to identify a group of parameters and variables which are going to have a effect collectively on the heat transfer, isn't it? So and that kind of groups can be found out directly by using dimensional analysis. So dimensional analysis is not completely a black box type of analysis. There is some physics is involved in it, isn't it? Because when we are saying that identify the relevant variables, identifying the relevant variables comes from not only the physical principles but also from our experimental analysis, isn't it? Correct. So if I increase a particular mixing, definitely the temperature within the system is going to become uniform quickly. This type of things we can easily predict based on our analysis of the experimental operations as well as from uh, the physical concepts, isn't it? So the first step is to identify the relevant variables based on the physics of the problem and also from the experimental analysis. Once we know exactly that these are the parameters which are going to be relevant in the given system, then the next step is to apply a Buckingham Pi theorem. So Buckingham Pi theorem says if the equation phi, which is related to x1, x2, xn equals to 0, is the only relation among the quantities x1, x2, xn, and if it holds for any arbitrary choice of the unit. So what it means is this particular relation is valid in all type of units. It is not that if you are changing from SI unit to some MKS unit, so your relation is going to change, isn't it? It's not. Your whatever the equation you are writing, that will be valid irrespective of what type of units you are looking at. Okay. So in such cases, the solution of this equation can be written as f pi 1, pi 2, pi m, where pi 1, pi 2, pi m are the groups, where these are the m number of groups, independent dimensionless products of x's. Here, how many number of independent dimensionless groups we will have for a given system, that we can identify directly by looking at how many principal or a primary quantities are being used in a given system. There are 7 principal quantities, but out of these 7 principal or primary quantities, how many are actually used in terms of the variables, parameters and properties, that we have to see. So we can a priori find out how many dimensionless groups are going to be important for a given system, isn't it? And then using the dimensional analysis we can find out, and once we know that these are the dimensionless groups which are important for a given system, we can make our correlation in the form of these dimensionless groups. So this is a very important thing. First step is to identify the variables, parameters and properties. Second step is to identify how many dimensionless groups are going to be there. Third step is to identify these dimensionless groups using Buckingham Pi theorem. And the fourth step is performing the experiments. If you are having the experimental data, then you wanted to correlate your experimental data in terms of these dimensionless groups. That is what the procedure is. Okay. So this is the example which we have seen. I will not go in a detail. I will quickly go through this. So here we were looking at the pipe flow through a circular pipe. So here we wanted to see how heat transfer coefficient is related to other properties. What we have found out from our experimental analysis and physical principles, that H is related to velocity, diameter of the pipe, thermal conductivity, specific heat of the liquid, rho is the density of the liquid and mu is the viscosity of the liquid. Again, we can put the dimensions here. And then since in this case, how many fundamental quantities are being principal quantities are being used here. So these are mass, time, temperature and length, isn't it? So 4 principal quantities are being used here, and there are n number of variables which are 1, 2, 3, 4, 5, 6, 7 are there. So 7n, small n is and 7 minus 2, 3, we are going to have 3 dimensionless groups in this case. So we can write down the expression pi 1, pi 2, pi 3 like this. Here, since there are 7 quantities are there and we have a choice of only writing 3 equations, so there will be a 3 variables which will be selected H, Cp and V to be varying in these 3 equations. You could have selected instead of H, you could have selected mu or some other variable, doesn't matter. But the only thing you have to note down is all these parameters alpha A1, A2, A3, A4 or B1, B2, B3, B4 or C1, C2, C3, C4. This has to be calculated in terms of the exponent of the variable which is varying across the equation. So that means this A1, A2, A3, A4 has to be calculated in terms of A5. Similarly, B1, B2, B3, B5, B4 has to be calculated in terms of B5, and similarly C1, C2, C3, C4 has to be calculated in terms of C5. So this is the procedure. This we have already seen, so we have found out that for the first case, if we put all the dimensions and find out their exponents, what we get is pi1 comes out to be hd by k. So hd by k is nothing but Nusselt number. Similarly, in the second part, what we have assumed that if we equate the dimensions of the second equation pi2, which is given here, this pi2, if you put all the dimensions corresponding to the variables of pi2 and equate to this pi being a constant, it will have exponent 0, all the exponents 0 here. So if we equate everything, what we get is Cp mu by k. So that is nothing but the Prandtl number. So pi2 comes out to be Prandtl number. Similarly, if we equate the dimensions of the third equation, so that is again pi3 if we equate for corresponding variables. So by equating their exponents, what we get is we get pi3 equals to dv rho by mu raised to the power c5. So this is nothing but the Reynolds number. So what we can say here is to analyze the heat transfer coefficient in a circular pipe, three dimensionless groups which are important are nothing but the Nusselt number, Prandtl number and Reynolds number. So my correlations, whenever I am looking at the correlations for the heat transfer coefficient, remember here H is embedded in this Nusselt number. So clearly all my correlations will be in terms of Nusselt number. So Nusselt number should be related to the Prandtl number and should be related to the Reynolds number. In what form? That form is not clear. Remember, this thing is very important. Buckingham pi theorem only tells about what are the different dimensionless groups which are going to be present in the correlation, but it is silent about the exact form of the correlation. So whether it is going to be a algebraic equation, whether it is going to be exponential equation, logarithmic equation, what type of correlation we are going to have, on that the Buckingham pi theorem is silent. It only tells about that these are the dimensionless group which are going to be related for this particular system, and nothing more than that. Nothing more than that. Is it clear to everyone? Okay. Am I audible? Hello? Hello?
Yes, sir, you're audible.
Okay. Sorry. Okay. So this is what we have seen so far. Now let us extend our analysis to a little bit further. Buckingham theorem, as I said, is silent about what form of correlation we will be having. So now for a given system, let us assume that arbitrarily, again I am saying arbitrarily, let us assume arbitrarily that a power law dependence is present between H and other remaining quantities. So H is the heat transfer coefficient, and I am having the other quantities like thermal conductivity, viscosity, density, diameter, specific heat, and velocity. So all these parameters are related to H in an exponential equation like this, where the exponents are beta 1, beta 2, beta 3, beta 4, beta 5, and beta 6, and there is a constant C outside. Okay. So constant C is put here outside. Okay. Now, again, let us do the same analysis as we have done earlier. So with the same analysis, the dimension of H we know, so that we can put it here, and again we can put all the dimensions corresponding to these variables. If we put it and equate the exponents, what we get is by equating the exponents, what we get here is for mass, we have in the first this, so that becomes beta 1 plus beta 2, similarly beta 3, and there is no mass present in the remaining quantities, so this becomes beta 1, beta 2, beta 3, and that is equals to 1. Just wait, I think I missed something. Okay. So in this case, M is 1. M is 1. If you look at the dimensions of the heat transfer coefficient, that is M mt raised to the power minus 3 and capital T raised to the power minus 1. Okay. Okay. Okay, now it is correct. Now it is correct. Okay. So similarly, we can, equate the exponents of other quantities, and what we get is these 4 equations, because we have only 4 primary quantities are there. So we will get 4 equations. But how many exponents are there? There are 1, 2, 3, 4, 5, 6 exponents are there. But there are only 4 equations. So clearly the exponents, any 4 exponents has to be given in terms of the remaining 2, isn't it? So in this case, again, arbitrarily we are selecting that beta 1, beta 2, beta 3, beta 4. We wanted to express in terms of beta 5 and beta 6. So if you do that, what we get is beta 1 equals to 1 minus beta 5. Similarly, beta 2 is obtained as beta 5 minus beta 6. Beta 3 is obtained as beta 6, and beta 4 is obtained as beta 6 minus 1. So all these obtained values of exponents, we can put it in this equation and find out how h is related to all. So if we put it in this equation, what we get is hd by k. If we put all these exponents here, what we get is, on the left hand side, we get hd by k equals to c into cp mu by k raised to the power beta 5 and dv rho by mu raised to the power beta 6. So that is nothing but Nusselt number is related to c into Prandtl number raised to the power beta 5 and Reynolds number raised to the power beta 6. In fact, this correlation is regularly used in the practice. If you look at the turbulent flow, the Nusselt number is given as 0.026, 0.023 Prandtl number raised to the power, Reynolds number raised to the power 0.8 and Prandtl number raised to the power 0.4. This is the correlation which is called as Ritter's-Volter equation, which we will see today is regularly used for finding the heat transfer coefficient. Now the question is, how come we got a exact form of a correlation which is so regularly used? So the point here to note down is, as I said in the starting itself, that Buckingham pi theorem is silent on the structure of this correlation. It only tells about what are the different dimensionless groups which are going to be there in the correlation. In what form? That form is not clear anywhere. Okay, that form is not been told by Buckingham pi theorem at all. Okay, but here we are getting a specific form of the correlation, and that is because we started with the power law expression. That is because we have started with the power law expression. So we have started with the power law expression, and that is because of that we are getting a specific form of the correlation here, where the Nusselt number is given as c into Prandtl number raised to the power beta 5 into Reynolds number raised to the power beta 6. Okay, is it clear to everyone? Hello, is it clear? Can we go ahead? Hello.
Yes, sir.
Okay. So let us look at some of these dimensionless numbers. So far we have only looked at the concept that we wanted to correlate heat transfer coefficient because we wanted to keep our life simple. I am not interested in getting a exact solution. If I am getting a 20% 70% or 80% accurate solution, that is good enough for me. I am not aspiring to get exact solution for a simulation which is running for ages. Instead of that, I wanted to get a approximate solution which is 70 or 80% accurate, but I will get it quickly. So that is what I am interested in, isn't it? As a plant operator, that is what the people are in the process plant interested in. They wanted to get the solution easily. They don't wanted to do it on a fancy high computing facilities which will run over the edges to get the exact answer. So exact answer we are not interested in. We are interested in a reasonably accurate answer, but quickly. Okay, so now based on that we started looking at if I am saying correlations I wanted to have, So what form of the correlation, or what are the ingredients of this correlation, that we get it from the Buckingham Pi theorem, isn't it? Correct. And there we have found out that we will have some dimensionless numbers, isn't it? Whenever we are looking at the heat transfer, these are related with the dimensionless numbers. So in case of pi flow, the dimensionless numbers which comes into the picture are the Nusselt number, Prandtl number, and Reynolds number. But when I'm changing the system to, let's say, from forced convection to natural convection, there I get a different number. There I get a Grashof number and Reynolds number, isn't it? If I'm looking at some other system, there probably I will get some different number. If I'm looking at, let's say, the flow of the liquid metal, in that case heat transfer by a liquid metal, in that case I am interested in a Peclet number, isn't it? So different dimensionless numbers are important in a heat transfer. The point which I wanted to appreciate here is dimensionless analysis have given us the information that different dimensionless numbers are going to be important when I'm looking at the correlations of the heat transfer, isn't it? And depending on what system I am looking at, these dimensionless numbers are going to be different. So let us look at different dimensionless numbers which are regularly, used in a heat transfer analysis. So the first dimensionless number is a Nusselt number. As I said, we have used this form earlier, but we have not looked at its physical significance, what it is. Okay, so let us look at Nusselt number. So Nusselt number is defined usually as HD by K or HL by K, where D or L is a characteristic length, or whatever the length you are looking at in that particular system. Okay, so this is Nusselt number is given as HD by K for a pi flow where D is the diameter. How it is defined? It is defined as a wall temperature gradient divided by temperature gradient across the fluid in the pipe. So Nusselt number is defined as a wall temperature gradient divided by temperature gradient across the fluid in the pipe. So let us look at how we arrive to this, definition here. So consider a heating of a fluid while it flows through a pipe of diameter D. So there is a pipe of diameter D in which the fluid is flowing, and it is heated by a wall of the pipe which is at the temperature of TW. Okay, so at a certain axial position, let the wall temperature be TW. So temperature of the wall is TW and the bulk temperature is TB. So temperature of the fluid, bulk temperature of the fluid is TB. Again, we are assuming that what wall is a is at a higher temperature than the bulk temperature. So TW is greater than TB. So in this case, the heat flux at the wall is given as, the heat flux in the wall is given as QR is given as K dt by dr, K dt by dr. So here in this case, you can see there is no negative sign because as we are moving from the surface of the wall to the center, my basically as I am moving from the center to the wall, that is the increase in the R. During towards the increase in the R, there is an increase in the temperature, isn't it? So therefore there is no negative sign here. Okay, so the wall heat flux is given as QR equals to K dt by dr, and that is exactly at R equals to d by 2. So that is exactly at the boundary of the wall and the fluid. Correct. So this is the wall heat flux. Correct. So now this wall heat flux should be same as the heat flux which we will obtain by convection, isn't it? So that is given as H TW minus TB. So this is nothing but the Newton's law of cooling, isn't it? And this is from the Fourier's law of heat conduction, isn't it? So heat conducted through the wall. So that is given as heat flux QR is given as K dt by dr at R equals to d by 2 should be same as H TW minus TB. Is it all right? Hello. So now we can rearrange the terms here. So we can rearrange the terms. So we can just add a D here. So HD TW minus TB divided by D. And now both these sides, this left hand side and the right hand side, we can rearrange a little bit. So we wanted to find out the Nusselt number. So HD by K we wanted to find out. So this is This is HD here. We wanted to divide only by K. So this K, which is on the left hand side, we can take it here in the denominator, and this entire factor TW minus TB by D, we will divide to this left hand side factor. So what we get is Nusselt number is given as HD by K, that is given as just wait. So I made the mistake. Okay. This K should not be there. Okay. Now it is okay. Okay. So what we get is HD by K is obtained as dt by dr at r equals to d by 2. So that is nothing but wall temperature gradient. Remember, this is nothing but a wall temperature gradient, numerator. Whereas denominator is what? TW minus TB is nothing but the change in the temperature taking place between the wall and the bulk. Wall and the bulk, isn't it? And I am dividing it by the diameter. So remember, wall, this entire thing is happening inside the diameter of the pipe. So what I'm trying to get here is the temperature gradient across the fluid pipe. So TW minus TB is nothing but the TW is nothing but the wall temperature, whereas TB is nothing but the bulk temperature, and I am this difference I am dividing by the entire cross section D. So basically what I'm calculating here is the temperature gradient across the fluid pipe, isn't it? So that is what the definition of Nusselt number is. It is the wall temperature gradient divided by, I am saying wall temperature gradient because this gradient dt by dr is calculated at r equals to d by 2. Okay. Is it all right? Is it clear to everyone? Hello?
Yes.
Okay. Reynolds number, again, I will not go in a detail that you have done it, several times in your other courses also. Reynolds number is a inertia force by viscous force. Inertia force can be rho v square divided by mu v by L. So that can be rearranged as LV rho by mu. Here we can write it in terms of diameter also. So that becomes dV rho by mu, depending on what we are looking at. Okay. Prandtl number again is a ratio of momentum diffusivity to thermal diffusivity, isn't it? So momentum diffusivity in this case is nu, that is nothing but the kinematic viscosity, which is nothing but viscosity divided by density, and thermal diffusivity is K by rho Cp. K by rho Cp, isn't it? So if you put it here, what we get is Prandtl number is given as Cp mu by K. Cp mu by K. So this gives me what is the physical significance here is, this gives me the information that remember what we have seen, the momentum boundary layer and the temperature boundary layer, isn't it? Thermal boundary layer. So it basically gives me how relatively these are with each other. That particular thing is obtained by the Prandtl number. So when Prandtl number is equals to 1, both are coinciding with each other. Okay, why we are looking at how close these are or how far these are? Because these are dependent on each other. Remember, the heat transfer depends on the fluid problem, and the fluid problem is also dependent on the heat transfer because it is going to change the values of my properties, isn't it? It is going to change my viscosity, it is going to change my density, and therefore my velocity distribution is also going to change. So whatever the boundary layer we are seeing in a momentum transfer, that is not independent. That also depends on the heat transfer, and in a way heat transfer also depends on the velocity distribution. Okay, so both are dependent. These are not independent. Okay. So that is why how far my momentum boundary layer and the thermal boundary layer are, this thing can be obtained based on the Prandtl number. Okay. Okay. Now let us look at the third dimensionless number. Third dimensionless number is a Stanton number. Stanton number is defined in this case as rate of wall heat transfer by convection, rate of wall heat transfer by convection, and divided by rate of heat transfer by bulk flow. Okay. It is given as H by rho V Cp. H by rho V Cp. H is a heat transfer coefficient, rho is a density of the fluid, V is the velocity and Cp is the specific heat. Okay. And that is given as Nusselt number divided by Reynolds number into Prandtl number. Okay. So now here let us look at this thing in more detail. So if you consider a temperature difference of delta T across the wall and the bulk fluid, convective heat flux is given as H delta T, isn't it? If the fluid flows at an velocity V, the rate of energy transport by a bulk flow or by movement of the liquid per unit area of the cross section, that is mass flow rate into specific into specific temperature change. So that is given as rho V Cp delta T. So what it means is, so convective heat flux, whatever is the heat transfer taking place by the convection, that can be given by directly by the Newton's law of cooling. So that is H delta T. And another factor which we are looking at is the how much amount of heat is taken by a bulk flow. Bulk flow. So that how much heat is taken by a bulk flow, that is calculated as rho v Cp delta T, because here mass flow rate is nothing but how much amount of heat is taken by a fluid element which is moving from a pipe. So that is given as mass flow rate into specific heat into temperature change. So that is given as rho v Cp delta T. Okay. So if we divide both these factors, what we get is H by rho v Cp. This delta T and this delta T get cancelled out. So what we get is H by rho v Cp. If we rearrange this equation, what we will get is Nusselt number divided by Reynolds number into Prandtl number. If you rearrange, so Nusselt number will be Hd by K. Reynolds number will be dV rho by mu. Prandtl number will be Cp mu by K. If you put it all this, what we will get is ultimately H by rho v Cp. So this is what we have obtained here. There is another number which is nothing but a Peclet number. Now Peclet number is slightly different than with respect to the Stanton number. In this case, the Peclet number is defined as rate of wall heat transfer by bulk flow. Rate of wall heat transfer by a bulk flow, which we have already calculated, isn't it? Bulk flow, this is what we have calculated, isn't it? So amount of heat taken by a bulk flow is rho v Cp delta T, and divided by rate of heat transfer by conduction. So rate of heat transfer by conduction is given by K by D delta T, isn't it? K by D delta T, isn't it? So that is what we have obtained. Remember delta T by D, that is going to give me the temperature gradient, multiplied by K is going to give me the heat flux. That is what we have obtained, the heat flux using the Fourier's law of heat conduction, isn't it? So delta T by D is nothing but the gradient into K is going to give me heat flux. So that is going to give me the rate of heat transfer by conduction. So if we rearrange all the terms here, what we get is d rho v Cp by K, and this is basically nothing but Reynolds number into Prandtl number. Peclet number is given as Reynolds number into Prandtl number. Okay. There is another number which is important when we are looking at the laminar flow, and that is a Grade's number. So Grade's number is given as Peclet number into D by L, where D is the diameter of the pipe and L is the length of the pipe. So this basically also accounts the wall effect here, isn't it? So D by L is going to give me how much is the diameter and the length ratio, isn't it? Okay, so these are the dimensionless numbers. There are some more dimensionless numbers, but that you can find out if and whenever we will come across this dimensionless number, we will see the physical significance of that. For example, there is a Grashof number. So Grashof number we will see when we will look at the natural convection. Okay, so in the next chapter where we are going to look at natural convection, there we are going to look at the Grashof number. So there are some more numbers are there, but that we will look at whenever these are coming in. Okay. Okay. So again we have started logically, isn't it? We start. Yes, please go ahead.
Sir, as you explain the physical meaning of Nusselt and Prandtl number, can you briefly tell the physical significance of Stanton and Grassett number?
See, so Stanton number here is, see, most of these correlations are given in terms of the Nusselt number, Reynolds number and Prandtl number. Here Stanton number is one more number, one more additional number, which accounts all three numbers, isn't it? So in a way, see, if you look at basically, so there are three numbers, Nusselt number, Reynolds number and Prandtl number. If you look at the Stanton number or even Peclet number, this is the combination of the other two, isn't it? These are the combination of other two. But why these are used? Why these are used? So rationale behind using these are, in some physical cases, in some physical cases, remember Buckingham Pi theorem is silent about the structure, isn't it? Buckingham Pi theorem is silent about the structure, but when you are making a correlations, in some cases this Nusselt number divided by Reynolds number and Prandtl number, this entire factor becomes important. This comes out directly from the experimental thing, isn't it? So there, in general, the Stanton number is used. Okay. Again, if you look at the flow of the liquid metal, so there this combined factor of Reynolds number and Prandtl number is more important rather than looking at Reynolds number and the Prandtl number. Why? Because see, when we are looking at the liquid metals, for them the Prandtl number is a very the Prandtl number, if you look at the value of the Prandtl number is very high in that case. Okay, so this entire factor is more important there. Okay, so in a way these are in a way a combination of the Nusselt number, Reynolds number and Prandtl number. But if you look at the physical significance as such, physical significance, these are only you can tell based on this particular the form which I have written here, that is nothing but only the rate of wall heat transfer by convection and rate of heat transfer by bulk flow. So what it means is how much amount of heat that is being transferred by a convection from the wall and how fast you are taking that heat by a flow. You understand?
Yes,
So
sir,
what
yes.
it is physically telling me how fast I am transferring the heat. Maybe if you look at, maybe I just give a cylindrical structure. Okay, I do not have here. Okay, I will give it in the next. Okay, so how fast the heat is being transferred from this wall here to this fluid here which is flowing inside, isn't it? With respect to that, how fast I am taking that heat out from this location. So these two things are compared in the Stanton number. In case of Peclet number, what is been looked at is rate of wall heat transfer by a bulk flow. So how fast I am taking the heat from the pipe or a channel, divided by how fast the rate of heat transfer is there by conduction. So these two things are important. Okay, let's look at what I'm trying to say here. So one Stanton number looks at the convection which is taking place in this pipe, okay, versus how fast the heat is taken by the fluid flowing. Whereas Peclet number looks at how fast the heat is transferred through this metal wall conduction. Okay. Just wait. Sorry. So in case of Peclet number, how fast the rate of heat transfer is taking place across this entire pipe, that is looked at based on the conduction. So remember, there are two factors. When heat is being transferred from, let's say, from top to here to the pipe, there are two factors. One is, see, when we are looking at the convection, it also counts the conduction. Isn't it? But suppose the velocity of the fluid is not very high. Velocity of the fluid is low and the flow is in a laminar region. So in that case, what will be more prominent? More prominent is going to be conduction, isn't it? Conduction across this entire pipe here. So that is looked at here in the Peclet number. So rate of heat transfer by conduction inside the pipe. This is inside the pipe. Remember, delta T by D is across the pipe. Delta T by D is across this pipe, isn't it? That is what it is being looked at. So these two factors are compared in case of the Peclet number. That's it. But in a essence, what you can see here is these are related only with Reynolds number and Prandtl number. Okay, even though we are looking at the Peclet number separately, we are looking at, but these are related to Reynolds number and Prandtl. Okay, clear?
Yes, sir.
Okay. Now, so far we have gone one by one. We have started with the argument that we want the heat transfer coefficients. Then we said that heat transfer coefficients should be in the form of dimensionless numbers. Then we have looked at the dimensionless numbers. Now let's look at the real part, how to calculate the heat transfer coefficient, isn't it? So experimental determination of heat transfer coefficient. So what we have to do, suppose somebody gives you a job. Suppose if you join some process industry and you are working on some new type of a fluid, maybe in a some new type of fluid you are using as a coolant or something. So in that case, what type of correlations you need to use if you have to develop, how you are going to develop. Okay, so the simple experimental setup to obtain the heat transfer coefficient is a double pipe heat exchanger. So this is a double pipe heat exchanger. There is a inside pipe is there. So this is a inside pipe where a fluid is flowing at temperature T1. The outlet temperature is T2. Again, this fluid is being heated by a saturated stream which flows through this annular region, which is outside this inside pipe. So there is a two pipes are there, isn't it? So inside pipe is flowing a fluid and outside pipe is flowing a saturated steam. Okay. Now what we are saying here is a correlation for the heat transfer can be developed only on the basis of a substantial amount of experimental heat transfer data for a particular system. So what we wanted to do here is we wanted to generate lot of data for a particular system, Okay, so in this case, if you are looking at the pipe flow, this particular pipe flow, then we will, this is the example of generating the heat transfer coefficient for the, obtaining the heat transfer coefficient for the pipe flow. So that is why we have used a double pipe heat exchanger where the heat transfer is taking place from the radial direction from the annular region to the inside pipe here. Okay. Again, lot of data has to be generated. So lot of data has to be generated because we wanted to have a range of variability in the variables which we are looking at, isn't it? So large number of fluids which we have to use. Instead of using a single fluid, we have to use a large number of fluids because we wanted to cover the entire range of density, we wanted to cover the entire range of viscosity, we wanted to cover entire range of specific heat and the thermal conductivity K. Sorry, this became okay. So clearly these are the material properties, isn't it? Rho, mu, Cp and K, these are the material properties, isn't it? Correct. So it's not possible for me to vary the density of water too much, isn't it? How much I can vary? It is going to vary only with temperature, isn't it? Other than that, I have no flexibility to vary the value of density or thermal conductivity, isn't it? So the only way I can have a different values of rho, mu, Cp and K is by having different fluids used in this heat exchanger. Is it clear? Is it clear to everyone what I'm trying to say? So this experiment has to be performed using large number of fluids in order to have a variability in rho, mu, Cp and K. Similarly, in order to account the variability of D, I need to use a different diameter of the pipe. So this is one diameter. I can have another diameter. So variability of the diameter I have to use by using a different diameter of the pipes. Also, the variability in velocity can be accounted by varying the velocity over a large range, isn't it? From the laminar region to turbulent region, something like that, isn't it? Then again, if I am using the steam here, steam is getting condensed and heat is being transferred here, isn't it? So that means the temperature of the fluid is changing across the length. So clearly the properties rho, mu, cpk, these are also going to change. So which values I have to use? I have to use the values at the average temperature. So the values of the fluid properties should be used at the average temperature T1 plus T2 divided by 2. So rho, mu, cp and k should be used at average temperature. Sorry. Okay. So now with this variability, we have to perform large number of experiments, and once we perform the large number of experiments, what we are going to note down is we are going to note down these temperatures. T1 inlet temperature we know, outlet temperature we are going to note down. That's it. Only inlet and outlet temperature we require. In this particular experiment, inlet temperature we know. For all the variabilities, we wanted to we will be measuring T2. Once we know T2 and T1, this wall temperature TW, this can be obtained directly. Because the saturated steam is used. So that means this temperature is going to be around 100 degrees Celsius. So that is already known, isn't it? So wall temperature is known. Then we can make a heat balance. So heat balance in this case is going to be what? The heat gained by the liquid through the inner pipe. So heat gained by the liquid through a inner pipe, that means what? Amount of heat that is being taken away by the fluid which is moving along this direction, along the axial direction, that can be obtained directly as pi by 4 d square. So that is nothing but the area into rho v cp into T2 minus T1. So this is nothing but the change in the temperature takes place at this end. So this is nothing but the sensible heat gained by the fluid as it moves from the right hand side to the left hand side. This is nothing but the sensible heat gained by the fluid. Now the sensible heat gained by the fluid is what? The amount of heat being transferred by the saturated steam to the fluid across this entire length. But the temperature at this end and the fluid temperature which is flowing through this pipe at this end and at the right hand side, both are different. That means delta T is going to be different. Here this delta T is going to be different. So whenever this delta T is not same across the length of the pipe, in that case delta T LMTD is used, log mean temperature difference. We will derive this part we are going to derive towards the end of this chapter. Okay, for a time being, let's assume that this delta T LMTD which I have used here in the Newton's law of cooling, which is nothing but H A delta T. Here instead of delta T I have used delta T LMTD. Why I have used delta T LMTD? That we will prove eventually at the end of this particular chapter. Okay, but for a time being, let's assume that I have written a correct expression. Why we are using delta T LMTD? The explanation I am giving here you is the temperature T here will be T2, isn't it? Saturated temperature will be TW. So temperature difference will be what? TW minus T2. Whereas the temperature difference at this end will be what? TW minus T1. So the delta T here at this location on the left hand side and delta T here at the location on the right hand side, this is varying across the length of the pipe. It is not constant. Whenever this delta T is not constant across the pipe, instead of this delta T, what we have to use is delta T LMTD, which is nothing but the log mean temperature difference. And the exact form of this log mean temperature difference, why this log mean temperature difference, we will prove eventually. That is what I am trying to say at this point. Is it clear to everyone? Hello? Hello? Is it clear?
Yes, sir, it's clear.
Okay, so this This is the energy balance which we have written here. This is nothing but the heat taken by the fluid. This is nothing but the sensible heat gained by the fluid, and this is nothing but the heat transfer by convection uh, to the fluid which is present inside the pipe. So delta T LMTD is again defined here is TW minus T1 minus TW minus T2 divided by ln TW minus T1 divided by TW minus T2. So this is nothing but log mean temperature difference. So in this particular equation, everything is known. The only unknown is H. Delta T LMTD we can calculate because T1, T2 we have measured, T1 we know, TW we know, delta T LMTD we can calculate. Diameter of the pipe we know, density of the fluid we can calculate as an average value, velocity of the fluid we know, specific heat Cp we can calculate as an average value. T2 and T1 these are known, everything is known in this equation, the only unknown is H. So we can calculate H. So once we calculate the value of H using this experiment which I have shown here, this experiment has to be performed over the large number of fluids by varying rho, mu, Cp, K. This experiment has to be performed by varying the value of D. This experiment has to be performed by varying the value of velocity V, and in all the cases we can find out H. So we know the value of H, we know the variation in these parameters rho, mu, Cp, K, D and V, and based on this now we can develop the empirical correlations in the form of this, isn't it? Because for a pipe flow in a laminar region, what we should get is pipe flow. For a pipe flow, the expression should be in this particular form. Okay, where Nusselt number is related to the Reynolds number into Prandtl number. Again, this form is not fixed, but the Nusselt number should be related to the Reynolds number and Prandtl number, that is fixed. So whether this is in a power law form like this or in some other form, it doesn't matter. It doesn't matter. Whatever the correlation fits for the data of H and the properties, based on that you generate the correlation. Okay. So this is what the experimental procedure to determine the transfer coefficient. Okay. Okay. Now let us again go ahead with one more step. We started with heat transfer correlations are required. Then we looked at the dimensionless numbers are should be there in the heat transfer correlations. Then we have looked at dimensionless numbers. After that, we have looked at how to calculate, how to obtain different correlations. Now let's look at different correlations which are already made by different people over the period. So there are different correlations which are already available. If you look at the heat transfer book, these are filled with lot of correlations. So people have already done. Heat transfer is a old subject. People have started looking at the heat transfer from the beginning of 18th century. So these correlations are readily available for most of the systems, unless you are working on some new fluid, something like if you are looking at the nuclear reactor or something where some liquid, some different liquid metal is flowing or something. In such cases you have to make your own correlations. Other than that, in most of the cases the correlations are already made by people. Correlations are already available in the open literature. Okay. So some of these correlations, some of these, the correlations which are regularly used, we are going to use, we are going to, discuss here. Again, as I said, there are, infinite number of correlations people have used. So if I give you a problem, if I give you a correlation there, it's okay. If I don't give you a correlation, you have to use a correlation which is given in this particular book, the transfer by BK Datta. Don't use the correlation, don't do the googling and then find out some arbitrary correlation from some other book or something and use it. You are going to have some variability in the answer, and I am not going to accept, because I have told a priori that one has to use only the correlations present in this particular book. I am not saying your answer is wrong or something. That answer could be correct, but for a uniformity in the correction, uniformity of the corrections of your answer script, I want to have a uniform answer. That is only the point I'm saying. I am not at all saying that the answer in that case is going to be wrong or right. That could be even, better than whatever the answer you could get based on the correlation which is present in the BK Datta book. Perfectly all right. But I don't want you to have a variability in your answers. There are 200 students, isn't it? If I start looking at the variability in each of the students, it is going to take 1 month for me to check the copies, isn't it? Okay. Is it all right? Hello? Is it clear to everyone what I'm trying to say? So please use these correlations present in the BK Datta book. Don't use it from some other random source. That is what the request is. Okay. Okay. So let us go. Hello. Is it clear? Am I audible?
Yes,
Nobody's saying anything. Okay. Okay, so let us look at the different correlations. So systems of various shapes and different flow conditions are encountered in practical heat transfer calculations. Yes. So we could have a, pi flow, we could have a flow across the cylinder, flow across the sphere, flow across the flat plate. We could have a situation where the pipe is a rectangular channel. It is not a circular pipe. So various shapes and different flow conditions like it could be a, laminar flow. It could be a turbulent flow. It could be a Stokes flow with a very low Reynolds number, isn't it? So everything, there is a variability in this, isn't it? So different correlations based on a geometry, based on the flow conditions, people have made it. Okay, so common shapes or geometries such as cylindrical, spherical, or a flat uh, uh, geometry, for these the correlations people have made. The most common flow problem involves the flow through a circular pipe. So the other important flow problems are the flow through a non-circular duct, such as a rectangular channel, through a packed bed, so which could be a catalyst packed in a packed bed reactor. Uh, in a agitated vessels where there is a agitator is moving continuously, there is a temperature probe is there, so there are internals present. If you look at the nuclear reactor, there are multiple internals are present to measure the temperature, spatial variation of the temperature across the reactor. So there are internals are present. Again, it could be a jacket flow, flow through a jacket over the reactor, or it could be a flow across the bank of tubes. Okay. So there are multiple, um, different heat transfer problems are present across. Okay. Again, a flow of a fluid in a system may be internal. It could be flow inside the pipe. It could be flow across the pipe, across the cylinder, something like that. Okay. So flow inside or external, this type of situations are also present. So let us look at a very simple case, that is nothing but a laminar flow through a circular pipe. So laminar flow through a circular pipe, the correlation given by Hansen, this correlation is given in 1943. Nusselt number is given as 3.66 plus 0.0668 into D by L into Reynolds number into Prandtl number divided by 1 plus 0.04 in the bracket D by L Reynolds number into Prandtl number raised to the power 2 by 3. And this is valid for the laminar flow. So that is why the Reynolds number should be less than 2100. For a pipe flow, the critical Reynolds number is 2100, isn't it? That is the critical Reynolds number, beyond which there is a transition zone, and beyond 10,000 there is a turbulent zone, isn't it? So again, here the Nusselt number is defined in terms of the diameter, so that is why it is given as hd by k. Similarly, the Reynolds number is defined as dv rho by mu. So h is a average heat transfer coefficient. Most of the time, the heat transfer coefficient which you get from this correlation, these are the average heat transfer coefficient. Remember, heat transfer coefficient can also change spatially as we move along, isn't it? But the idea is to report the average heat transfer coefficient so that calculation become easy. Then it becomes the average heat transfer coefficient into area into delta T. That's it. Okay. Again, one more thing which I have not written here that I have to check probably. This particular correlation is valid when there is a constant heat flux, constant wall heat flux. Let me check whether that is whether I am saying it correctly or not. This particular correlation is valid for constant heat flux. Just give me 1 minute. I'll just quickly. So this particular correlation is fully developed flow and a constant temperature of the pipe wall. Constant temperature of the pipe wall. Sorry, this is for a fully developed flow and a constant temperature of a pipe wall. This is very important statement. Why this is very important? We will come to. This is for a fully developed flow. Fully developed and constant temperature of pipe wall. Okay, this statement is very important. Why this is very important? We will come to very soon. Constant. I will just make it with some different color. Okay.
Hello, sir.
Yes, please go ahead.
Sir, can we leave a little early today? We have an important quiz at 11.
I will complete it in 5 minutes. Yes,
Yes,
no
sir.
problem.
So can you also please tell us what the syllabus for the
Syllabus
upcoming
will be whatever we will cover till today. That will be the syllabus.
All right.
Okay, I will take 5 more minutes and then we will stop. Okay, one more slide I have to complete. I have 3-4 more slides, but probably we will complete it in the next. Okay, so let us not delay the discussion. So the point here is this correlation is valid only for fully developed flow and constant temperature of the pipe wall. This is very important because this 3.66, you can prove that for a Stokes flow, for a laminar flow, you can analytically prove that Nusselt number is equal to 3.66. In fact, for a constant wall temperature, we get 3.66, and for a constant heat flux, for a constant wall heat flux, we get 4.364. So Nusselt number equals to 4.364. That is what you get when we are using a constant wall heat flux. So remember, these correlations are not arbitrary. This 3.66 Nusselt number equals to 3.66, that we can analytically prove. In fact, one of such proof I will give you. I will give you one of such proof maybe in the next class, so that you will appreciate that these correlations, even though Buckingham Pi theorem says that it should be related to Reynolds number, Prandtl number and Nusselt number, but still some more physics is involved in this. Some more physics is involved because people have solved a simple problem analytically. Whatever the final expression they have obtained, the correlation they have developed something similar to that. Something similar to that. So these correlations, all these correlations which are made by the people, these are not completely arbitrary. There is some physics is involved. Okay. Okay, is it clear? There is another correlation given by Cedar and Tate. This is a simpler correlation, but there are some conditions are also there. So that means the Prandtl number should be between 0.48 and 16700. Also mu by mu w, that should be between 0.0044 to 9.75, and Peclet number into d by l, that should be greater than 10 raised to the power 8. So these are the different things which are the different conditions which we have got. One has to check when they are interested in applying the second correlation given by Cedar and Tate. Okay, so let us move to the next slide. Sorry, let us move to the next slide. In a turbulent flow through a circular pipe, the correlation which is used is a Ditters-Boelter equation, and this is one of the most famous expression. Everywhere people use this Ditters-Boelter equation. This is used for a turbulent flow. Remember, these two correlations are for a laminar flow through a circular pipe. And again, if you use a Stokes flow with fully developed flow and a constant temperature, then you get Nusselt number equals to 3.66. That's it. Okay, one of such problem I have given in last year exam, where there is no nothing is given, only the Nusselt number is given and one has to calculate H, that you can directly calculate from this factor. Okay, so the most famous equation which is used for the turbulent flow is a Ditters-Boelter equation. That is given as Nusselt number is given as 0.023, Reynolds number raised to the power 0.8 and Prandtl number raised to the power n. For heating, when TW wall temperature is greater than the temperature of the fluid, in that case the exponent is 0.4, N is equals to 0.4. For cooling, when TW is smaller than the bulk temperature of the fluid, in that case the N is 0.3. Again, the condition for applicability is Prandtl number should be between 0.7 and 160, D by L should be less than 0.1, and Reynolds number should be greater than 10,000. Remember here, in a turbulent flow, the Reynolds number is greater than 10,000. Again, this is applicable only for a moderate range of Prandtl number. But when we are looking at the Prandtl number in case of some material, the Prandtl number could be very large also, 16700 something. In that case, a slightly modified form of the Dittus-Boelter equation, which is given by Cedar and Tate, should be used. So this equation is 0.023 into Reynolds number. Sorry, Cedar and Tate equation, there is some changes there. I'll just correct. I'm sorry. This is 0.27. Okay. So 0.027 Reynolds number raised to the power 0.8 and Prandtl number raised to the power 0.33 into this additional factor is used, where mu by mu W is nothing but the ratio of the viscosity at the bulk and the wall, and raised to the power 0.1.
Excuse me, sir. I think
yes,
your screen is not visible.
My screen is not visible. Let me share it. Okay. Is it visible now?
Yes, sir.
So there is a modified expression which is nothing but a Cedar-Tate expression when I am having a higher range of Prandtl number. This particular Dittus-Boelter equation is valid only up to 0.7 to 160 Prandtl number, isn't it? But this another equation, Cedar-Tate equation, is valid for a higher range of Prandtl number. So there is an additional factor coming in, which is nothing but mu by mu W. So this basically accounts the viscosity at the bulk divided by viscosity of the viscosity present near the wall, viscosity of the fluid present near the wall. Okay, clear? So this is applicable for a large temperature difference, whereas the Dittus-Boelter equation is applicable for a moderate temperature difference. Again, there is a last correlation which is used only for the liquid metals flowing through the pipe. So this equation is given by Siban and Shimazaki. So Nusselt number is given as 5 plus 0.025 Peclet number raised to the power 0.8. Again, I am coming back to the same point. If you solve this particular problem analytically, what you get is Nusselt number equals to 5. So this 5 coming in here, 5 plus, that is not arbitrary. There is some physics is involved. Okay. So we stop here. One of the proof of laminar pipe flow when there is a constant heat flux, we will do it in the next class. Okay, so that correlation comes around. Nusselt number is given by 0.4.364 and for a constant wall temperature it is 3.66. So the second part we will not derive. You can find out in several books, but this first part we will derive in the next class. So we stop here. So whatever we have done so far will be the syllabus for the quiz on Monday. I am going to upload all these slides in the MS team. Okay, today. Clear? Is it clear to everyone?
Yes, sir.
Okay. So we stop here today. The quiz will be again on the Moodle. The quiz is going to be on Moodle. Okay. So please check whether you are enrolled in the Moodle or not. I don't want you to, saying it later that my name is not appearing in the Moodle. That should not happen. So please check whether you are enrolled in this course on Moodle or not. Okay.
Yes, sir.
Okay. We stop here and let us continue on Monday. So Monday we will have a quiz, but we will have a tutorial on Monday. Okay.